Hello, everyone. Very excited to be here. So I'm Bobbin from Polygon, specifically leading Polygon Maiden effort. And today I'm going to talk about AirScript. So AirScript is a domain-specific language for writing and auditing error constraints for Stark proving system. And today during the talk, I'll do a couple of things. So first thing, I would like to kind of explain what error constraints are, and then talk about AirScript specifically, explain why we have it, and give an example, or actually give a kind of quick intro into syntax of AirScript, and then give a couple of examples. So let's start with error constraints. Before I actually dive into specifics of error constraints, I would like to kind of lay out the bigger context. So when we want to generate a Stark or a Snark proof or an EZK proof for a computation, we usually go through this process of optimization that takes a computation and translates it into a set of statements about degree-bound polynomials. And in case of Stark proving system, this, what we get at the end is representation in polynomials is called algebraic intermediate representation, or AIR for short. So AIR, that's why it's called AirScript. The way this fits into overall Stark proof generation process is as follows. So in the Stark proof generation process, we start with an execution trace. We do something that is called a low degree extension. And by the way, this is kind of skipping a bunch of like smaller, simpler steps here, but this is kind of like a high level view of the process. So we do a low degree extension. Then we evaluate constraints over this low degree extended execution trace. We compose them, and for efficiency purposes, into a single composition polynomial, and then we prove the degree of this polynomial using Fry protocol. The error constraints come in this step specifically when you do constraint evaluation. So when you have this extended trace and you apply the constraints to this trace, this is the stuff we care about. So error constraints consist of a few things. Specifically, they're actually, you can think about them as rational expressions, but it makes sense to kind of break them into different types. So first type is boundary constraints. And these boundary constraints basically assert that a specific cell in the trace has specific value. Like in this case, for example, I'm asserting that first cell in the first row has value x, and third cell in the last row of the trace has value y. This is useful frequently for expressing kind of like input and output conditions of a computation. The other thing that, the other type of constraints that we usually have is what we call validity constraints, and this impose some validity conditions on cells in a single row. So you can think of them as a function that takes one row of a trace as an input and then outputs a 0 if the constraints are valid, or non-zero if there is a violation of some constraint. And last type of constraint is transition constraints. They basically enforce relations between consecutive rows of the trace. In the simplest form, if you take two consecutive rows and you basically run them through this constraint, again, the constraint function should output a 0 if the constraint is satisfied, or non-zero if it's not. And this is a kind of critical part of the entire constraint proving system. If all constraints are satisfied, all these functions should output zeros. To give a more concrete example of how this works, so let's take this Fibonacci example, a very specific computation. This is like an example of a trace for Fibonacci function. I'm assuming everybody knows what a Fibonacci function is. But in here, we have a slight twist on this. We use two columns to represent Fibonacci function, so it kind of like zigzags through this column. So 1, 1, 2, 3, 5, 8 is the sequence that we want to represent, and kind of like moves from one column to another. And what we want to assert in boundary constraints, for example, is that first two cells start with 1, so we will have boundary constraints, and then we want to assert that the last value of the Fibonacci sequence is whatever we computed. And then we have a very simple transition constraints as well, which say that the sum of previous two values, or the next value, is equal to the sum of the previous two values in the sequence. And these constraints here do that. So using this set of constraints, we can, prove, somebody can prove that they've computed Fibonacci sequence, and somebody else can verify that the answer is correct. So they don't actually need to run the Fibonacci sequence themselves. They can just take these constraints, verify them against the proof that the prover generated, or apply them to the proof that the prover generated, and be convinced that this, 2, 8 150 and so on value is the right result. So why do we want to work on AirScript? Why AirScript in the first place? This is kind of another view of the start proving and verifying process, and basically this is to illustrate, so like the top part is similar, although simplified to what I showed before, where you have execution trace, it goes into the prover, the proofs comes out. But there is another part of this where the verifier also needs to have constraints. And you can see that here constraints are used in two different parts. So it's the same constraints, and you need to use them for the prover and also for the verifier. In Maiden, we may have different verification contexts. So for example, we want to have verify constraints as a regular verification for using Winterfell. This is the proving library we currently use. We may want to verify constraints recursively for recursive verification within Maiden VM. This is to verify recursive proofs. We may also want to verify proofs on Ethereum at some point, and for whatever reasons. And then we need to have the same constraint evaluation logic encoded in Solidity. And these are all kind of, we want to have one set of constraints that we can kind of like evaluate in various contexts. And then, as I mentioned, there is also the prover that also needs to know about the constraints. So this means that, ideally, rather than writing constraints in all of these different contexts and different languages, we want to have just a single place, a single source of truth, where we would write constraints where they can be maintained and audited and all of that stuff. So the basic goals of AirScript, just to lay them out, is we want the constraints to be readable. The constraints are easy to read, and for both developers and auditors. Ideally, you don't need to learn a new language like Rust or some low-level language. So you can just keep it as close to arithmetic expressions as possible, algebraic expressions. We want them to be powerful enough to describe the needs of at least Maiden VM, but if it applies to more general and more complicated circuits, that would be nice as well. And we want them to be modular, so we want to decouple kind of the representation of constraints from kind of the optimization steps and all, and the target against they will need to be evaluated and supported on. And just to lay out more explicitly the benefits of this modular approach. So if you start with kind of AirScript source code, and then we also have AirScript intermediate representation, and we can have multiple backends for different systems, whether it is prover or verifier. We can have Winterfell, Maiden assembly, Solidity. There could be other backends for different purposes. And they kind of have different concerns. The concern of the source code is to be very readable, so you should be able to read things very easily, and for auditors to be able to view them and verify that or understand what the constraints do. You want to have some optimization happen at the IR level. And one of the things, for example, right now we have our constraints expressed in Rust, and one of the tensions there is that the more readable you try to make something, the less optimized it is. And the more you optimize something, the less readable it is. So this setup is meant to address that, where you can keep things readable on the front end and still have optimizations done at the IR level. And then for specific backends, you can have different optimizations as well. The way you would optimize things in Rust will be different from the way you optimize things in Maiden assembly and Solidity and other places. So now I'm going to go a little bit into the overview of how AirScript works. So first, AirScript source file consists of multiple sections. First section is declaration of a trace, so that execution trace that I mentioned before. You can think about it as a two-dimensional matrix with columns and rows. So the trace declaration defines the shape of the execution trace. Then you have public inputs section that defines what public inputs do you expect to provide to the circuit. There's boundary constraints that I mentioned before, and there is the integrity constraints, what we call a single thing for specifying both validity and transition constraints. And to give more concrete examples, so for example, this is a trace declaration. You declare trace columns. We currently support two different segments. There is this notion in Starks where you can have main trace and you have auxiliary trace, and you can define how both of them look like. You can name different columns, so A, B, C, D are actually names that we give to columns, so you can refer to them easily, so you don't say column 1, column 2. And you can actually name groups of columns as well. That's very useful in many cases. You can define periodic columns. These columns are something that is very efficient for the verifier to evaluate. So they're not quite free, but almost free, but they can be used as selector flags in many different situations. You can also have these random values. The random values, if you're familiar with how Starks, for example, work, after you commit to the main trace, you generate some randomness, and then you can use this randomness in constraints for the auxiliary trace. That allows us to do like non-local constraints, permutation checks, multi-set checks, and so on and so forth. Public inputs section currently is very simple. You can declare an unlimited number of public inputs. Each input could be an array of multiple values. Those have to be fixed size, defined size arrays. And one thing that we're currently working on, which we haven't yet finished, is variable length inputs, where you can have tables of fixed number of columns, but variable number of rows. Boundary constraints are fairly simple as well. You can basically have, you can specify what the first or the last value of every column is using the first or last keyword. And you can set those values based either on some constants, like 0 and 1 here. So like we're saying that, by the way, ENF or ENF keyword is used to enforce a constraint. So first value in column A should be 0, and first column in column B should be 1. And then we can also reference public input. So we would say whatever the last value is in column B is should equal to the, this first value in term value public input defined previously. So like if I go back, term value was one of the things we defined here. So integrity constraints now, this is what describes, I would say, almost the meat of the constraint system. Usually, like they take up much more logic than anything else. But here we can use, we combine both validity and transition constraints, and like let's say A prime here is the next value in a given column. So like A prime would be next value in column A, B prime would be next value in column B, and just B and A would be just values in the current cell. And here we can express, so like nth A prime equals x plus 1 just means that we take the next value in column A must be equal to x is the variable here, which is A plus B, so A plus B plus 1. And we can use also this, we have all the common arithmetic operations, so addition, multiplication, subtraction. We can also access all trace columns and random values in here. And we have this, like the first statement here allows you to define this intermediate values that makes, simplifies, if you have common sub-expressions and so on and so forth. We also have a syntax for list comprehension, like the second to last constraint allows you to apply this for, let's say, y is a set of columns, like a group of columns, so you can apply the same constraint very easily to a group of columns. So this is some of the examples of integrity constraints. So let's go through a simple example of how we would do, for example, that Fibonacci sequence constraints in AirScript. So we specify the name of the air, then we need to define our trace columns. If you remember, we had 2 columns, A and B, in the main trace. We didn't have auxiliary trace, so this is a very simple computation, doesn't need non-local constraints. We have public inputs. In this case, we will only have a single public input, which is the result of the sequence. Boundary constraints we want to enforce is that the first column is, the first values are 0 and 1. I think in the example I used 1 and 1, 0 and 1 could be used just as well. Just starts at a different point. And then what we want to enforce is the last value in the B column is equal to the public input that we provided. Then we have our integrity constraints, which are basically copy and paste from the constraints that I showed previously. So you have next value in column A should be current values from column A and B, or some of the current values from columns A and B. And next value in column B should be sum of the current value in column B plus the previous value from column A. Or actually, sorry, I said it backwards. The next value in column B should be previous value from column B plus the next value from column A. Sorry for confusion. This is some basic syntax. Like in AirScript, this is powerful enough for most of the things, but it would still be fairly tedious to write constraints using just this basic syntax. So we have a few things. One example is we allow constants, and this is both. You can have like scalar constants, like single value. You can have vectors. You can have matrices as constants. So in this case, we have like two constants defined. We can define what we call pure functions that just abstract away some computations. So in this example, like apply MDS function. And syntax here maybe looks a bit more complicated, but it's basically doing matrix vector multiplication. Yeah, this is what we use, for example, in hash functions. And you will see, in fact, this is constraints for rescue hash function. So we have apply MDS and apply inverse MDS, which takes a state of 12 elements and applies an MDS matrix to it, or inverse MDS matrix to it. We don't have this right now yet, but we will have support in the future where you can offload some computations to Rust. So some things may be expensive, or there might be better ways to do it, which we cannot express in AirScript to compute. And we can do this on the prover side. So for example, we would say instead of like doing this natively in AirScript, you can go find the Rust module that has the same function implemented and use more efficient implementation that relies on some other arithmetic that we can't express in AirScript to evaluate this. This is an optional feature for optimization only, and the verifier does not use this optional feature, but the prover could. And then we have the constraints here. So like this evaluator functions, you can abstract away. So instead of just having a single monolithic set of constraints, you can say, okay, this evaluator, the EV keyword stands for an evaluator, can evaluate constraints for a specific computation, or standalone module, so to say. And this, in fact, is evaluate rescue prime. And the last thing there is enforcing the constraints. So you see that this is all you need to do to express constraints for rescue prime hash function. And they fit on a single page here. So it's pretty simple. The other thing that we have in AirScript is modules. So it would be very, very inconvenient if you had to write, like for especially a medium to a large size project, to write all constraints in a single file. So you are able to split it into multiple files. So in this case, we can define this rescue prime computation as a module and put it in a separate file. And then, we can import it, for example. So like we define here, and we can say, okay, use rescue prime constraints from a different module. And then when we write, let's say we have this concept of chiplets, which is like accelerator circuits for the VM, for Maiden VM. And then you can use this rescue prime as one of the chiplets, for example. And the one thing you would do is you would basically make a call to this evaluator that you define in a different module. And you can do other things in here as well, like evaluators for other modules. Yeah, so you evaluate rescue prime, then you have more complicated, it allows you to do like compositions of different modules together. So like that's a very easy way to compose constraints together. And this is not going to go into all Maiden VM constraints. We'll explain. I'll show just like a basic construction because Maiden VM constraints are probably more than I can cover in a half-an-hour talk. But this is roughly kind of how like the execution trace for Maiden VM looks like. There are different parts of the trace. All of these parts are linked together with constraints. I'm not going to go into different parts, but actually, like on the right-hand side, this is the chiplets. I don't have pointer, I don't think. Maybe I do. I'm not sure. Yeah. On the right-hand side, there's like the chiplets, which contains the hasher, bitwise operations. You have a stack in the middle. You have a program decoder on the left-hand side. If we think about this, like when we want to define Maiden VM constraints, so we would have like a project, and we will import like system constraints, decoder constraints, stack constraints, range checker, chiplets, and all of that stuff. And all of the constraints for them will be defined into individual modules. And then we would say, okay, now we have our main trace of the entire, like the picture that I showed on the previous slide, basically has a set of like, I think in this version of the slide, because it's for slightly order VM, I think there's 74 or 75 columns here if you add them up. So like there's system columns, decoder, stack columns, and so forth. So this is how a trace looks like. There's auxiliary trace, which is used for this permutation checks, as I mentioned. So it's a more complex system. We need this auxiliary trace as well. And then we define our public input. There is program hash, stack inputs, a few other things. And then, our boundary constraints. I'm going to skip them for now. And we have integrity constraints. And what integrity constraints do, for example, we want to apply system constraints to the columns in the system trace. So we just say, OK, enforce constraints to the system constraints that we imported above and pass system columns into it. For decoder, we need decoder constraint and decoder tables. And this is for permutation check. So we'll pass that into the decoder module, and so on and so forth. So like you can see that at the high level, this is actually fairly simple. Like you kind of are able to modularize the system very, very well, where you have like one main driver module, and then you have sub-modules with different, different kind of parts of the system described in them, and then you can break them down even more and describe subparts of those. So it should be much easier to maintain that a single monolithic description of constraints. Or, again, we try to do this in Rust directly, and it works, but it is like not readable. I don't know how like anybody would go and audit our constraints in Rust, but like once we have AirScript, for example, we'll be able to like much more easily do audits and like maintain, if we want to change something, update the design of the VM, we need to modify the constraints. We do it in one place. We regenerate constraints for main prover, regenerate constraints for recursive verifier, regenerate constraints for verifier in different other contexts. So it becomes much, much simpler. All right, this is my talk. Any questions? I think there's a question there. Not sure if there's a microphone or you just shout. Yeah, so sub-circuits proven in Rust, the optional thing that I showed you where you can specify the Rust file, that's what you mean? Yeah, so they are used only for the prover. And the idea is that for the verifier, you use the main definition of whatever is provided in AirScript. And the prover is free to provide whatever they want for efficiency purposes. And the reason why that's OK is because if the prover tries to do something different and the computation doesn't align, the verifier will just not accept it. So the important thing is for the verifier to be correct. The prover can provide optimized versions of computations as much as they want. So they're not part of the verification process. And we don't care necessarily about if prover doesn't do anything as they should, if the system is correctly designed, then the verifier will catch it.
Any other questions? Okay.
Awesome.
Thank you, Bobbin. One round of applause for Bobbin.
Thank you.